Thank you, Franz. First off, I'd like to thank the organizers for inviting me to be here. It's my first time in India, and it's been a really great conference and visit so far. So for today's talk, some of these objects we're discussing might be a bit unfamiliar for probably a lot of the audience, but I hope you'll stay with me and we'll see maybe there's a very interesting story here. Here's an outline for today's talk. At the beginning, there'll be a rather lengthy motivation section where we discuss the notion of GX structures, and in particular, this kind of fibered GX structures, which will be after. And then after we have all the appropriate background and setup, I'll state the main theorem that we're heading towards. And then when you see the main theorem, there'll be lots of words I have to define. So in sections 1 and 2, we'll introduce the necessary objects for the talk. So no background is assumed on this Lie group G2 prime. I'll tell you right context. And then we'll discuss these pseudoholomorphic curves in the pseudosphere, S24 hat. And after that, we'll discuss the main theorem. Section 3 is a meet. We'll explain the main theorem in this explicit construction where we'll convert these equivariant pseudoholomorphic curves into these fibered geometric structures. And then in section 4, we'll see a second perspective on the developing map, which looks quite different, and we'll see some different objects come into play. So our story begins on a closed surface. So for the rest of the talk, S is always a closed surface of genus G at least 2, like our genus 2 surface here. So why do people always make this assumption about genus G at least 2? Well, that's because these surfaces admit a hyperbolic metric, so constant curvature -1 metric. And so what happens when you equip a surface with the hyperbolic metric is it has a special structure now. So hyperbolic surface is locally isometric to hyperbolic 2 space. So when you equip the surface with this hyperbolic metric, what happens is you get a refinement of the usual atlas as a smooth manifold. So instead of having just charts to Euclidean 2 space with transitions that are arbitrary diffeomorphisms, now what we can do is just consider all local isometries to H2 and all transitions between those local isometries. So those transition maps will be themselves local isometries of H2, which are each restrictions of a single global isometry. So in particular, all the transitions live in PSL2R, which is the orientation preserving isometry group of H2. So the transitions are locally constant. This is a very special structure. And so what we see is that the hyperbolic structure on a surface is just a specific instance of a more general notion, which is that of a locally homogeneous GX structure. So for the rest of the talk, the words locally homogeneous will be implicit. But what do I mean by this? It's just a generalization of the structure we discussed. So we have some manifold M, say smooth manifold or topological manifold, and a GX structure on M is a special atlas. Here, G is some Lie group, and X is some homogeneous G space. And you should think of X as replacing Euclidean space, so X is some model space, and G is some group of symmetries acting on X. And you have an atlas of charts of local homeomorphisms to the model space X, and the transitions are locally constant in G, just as we saw above. So this is the kind of structure we're after, and more generally than hyperbolic structure on a surface, you can think about constant sectional curvature, Riemannian manifolds as being an example of these locally homogeneous GX structures. All right, so as you learn whenever you study smooth manifolds, you never want to actually work with an atlas with your bare hands. So there's a notion of a development holonomy map, development holonomy pairs, which gives a way to globalize the GX structure on the manifold. So the first thing you do is you pull back the atlas from the manifold M to the universal cover M tilde. And the universal covering map is a local homeomorphism, so now you have a nice atlas of charts on the universal cover. And then you produce what's called the development map that globalizes the whole atlas into a single map. Okay, how do you do that? Well, what you do is just choose any chart in the atlas and declare the developing map on that chart, say U alpha tilde, to be the chart, say phi alpha tilde. So you've defined it on an open set. And what you'd like to do is basically push that out, propagate it out so that you have a global map on the universal cover. And the way you can think of doing that is, if I zoom in here, choose some point inside U alpha, call it X, and then choose any other point, Y, in the universal cover. And we want to define the developing map at Y. So how do you do that? Well, you take some path from X to Y, then you can cover that path by a finite number of charts. And every time two charts overlap, by definition of being a GX structure, the two charts differ by a single element of G on the overlap. So you just change the chart on the overlap by the appropriate element of G, and now the map is well defined on the intersection. And you do this and you propagate it along the curve. And what you can show is that, okay, it didn't matter which curve you picked, and it's independent of all choices. So in this way, in short, you real analytically continue, and the developing map becomes a global map on the universal cover. But it's not an arbitrary map. What you realize is if I take this development map I've built, if I restrict it to a small open subset, it agrees on the nose with one of the charts for the atlas. So this is a very special map. The development map is carrying the entire atlas all at once. Now the next thing you do is you examine how the deck transformations of M, pi1m acts as deck transformations, and how that interacts with the development map. And that leads you to the notion of holonomy. So, which I think we were alluding to this idea earlier, but when you precompose a development map by some deck transformation of an element gamma in the fundamental group, what happens is the development map changes by postcomposition by some element of G, which is called the holonomy of gamma. And there's a representation of the fundamental group that just records all of these global changes to the development map. So that's a representation from pi1m to G. And what we saw above is that essentially this pair, the development holonomy pair, is encoding the GX structure. So you can go back and forth, but not on the nose. You have some G equivalents, G orbit of equivalences. So here's the upshot of this discussion. Instead of working with GX structures in the sense of charts and atlases, you can work with development holonomy pairs up to the G action. So what happens is if you change the development map by left composition by an element of G, you didn't really change the GX structure. And when you do that, you change the holonomy by conjugation, which I denoted by CG. Okay, so in particular, since the holonomy changes by conjugation, this leads you to think about the so-called representation variety, which was introduced in the last talk. So I will call you look at the set of representations, just group representations from pi1m into G, and then you quotient by conjugation. I'll call that the representation variety. Although in many contexts, you want to restrict to some nicer locus of representations, maybe the reductive ones, as in the last talk, but I'll sweep that under the rug for today. All right, so now that we have development holonomy pairs, let's return to hyperbolic structures on a surface. We have some hyperbolic structure on the surface. It has a development holonomy pair. So we can think about what does it mean that this representation, look at the representation rho, the holonomy. That's a representation into PSL2R, but that's a very special representation. Think about how the deck transformations act on the universal cover. That's a group of properly discontinuous transformations. So this is a discrete and faithful representation, this representation rho, and that's fundamentally a geometric object. Because what the representation rho is telling you, it's telling you how to build a hyperbolic structure. If you take H2 and you quotient by the image of the representation, that gives you a surface homeomorphic to the original that's equipped with a hyperbolic structure. So rho is telling you how to build a hyperbolic surface. Rho is itself a geometric object. And our goal for today's talk is to generalize this to some other settings. So given some surface group representation from pi1s into some other Lie group G, can we realize it as the holonomy of some geometric structure? Can we geometrize it? Well, when you think about this question, you realize that there's a number of indeterminants that you need to fix. You need to choose some Lie group or class of Lie groups you want to work with. You need to choose what kind of representation you want to geometrize, because maybe an arbitrary representation can't be the holonomy, right, if it's not even discrete and faithful. You need to choose what kind of homogeneous space X you want to work with. And the most important and subtle question, you need to determine what manifold should carry the geometric structures. And maybe that just seemed obvious in the last example, right? To have a representation of the surface group, so of course the geometric structure lives on the surface. Well, it's not so subtle. It's not so easy in general. So you can imagine you can't make these choices arbitrarily. The choices you make in these questions 1 through 4 need to fit together in a way if you're even going to be able to obtain a solution. So now I'll say some words about the way this problem is approached in the field of higher rank Teichmuller theory. It basically just means the study of surface group representations into higher rank Lie groups. So what class of Lie group should we work with? Well, for starters, we need a non-compact Lie group because we want a discrete and faithful representation. And then we want some reasonably well-behaved class of Lie groups. So maybe we impose a reductive or semi-simple, make our lives easier. And I said higher rank, so tautologically, we need the real rank of the group at least 2. And a classical case that's more well studied is a case of real rank 1 groups, like PSL2R. Maybe you study hyperbolic surfaces in technoid theory, or PSL2C, maybe you study hyperbolic 3 manifolds. Okay, which representations? Well, this is a very hard question, but one that's been kind of worked out. So in 2004, Francois Laborie introduced the notion of an Anosov representation in a really groundbreaking paper. And this Anosov condition is supposed to serve as some strongly discrete and faithful. It's some generalization of convex co-compactness to the higher rank setting. So what we saw earlier is that, well, it turns out that every discrete and faithful representation into PSL2R is the holonomy of a hyperbolic structure. So discrete and faithful was the right condition in the rank 1 setting. So now in the higher rank setting, what can we say about this Anosov condition? Well, I'll tell you, I won't give you a precise definition because that's kind of a whole can of worms, but I'll tell you a few important properties. For starters, the Anosov condition is an open condition in the representation variety. So if you have a representation that's Anosov, then some open neighborhood of it is also Anosov. Moreover, the Anosov condition implies discrete and faithful, but it's much stronger than that. And third, you can think about the Anosov condition as being characterized by the representation having really strong singular value gaps. You recall the singular values are like the eigenvalues, but not exactly. So eigenvalues of A times A transpose. Okay. So which homogeneous G space should you work with? Well, that's a bit of a loaded question because it depends on your interests. But the most common answer is to work with these so-called flag manifolds, which are a special class of G homogeneous spaces that are in particular compact, and they're also projective varieties. And I guess that stands in contrast to, in the rank 1 situation, the most common answer is a symmetric space, say H2 for PSL2R or H3 for PSL2C. Okay, the most important question, which manifold? So before I say any more words on what are the right conditions, let's just think for a second. Suppose we have a group, say PSL4R. This group doesn't have any 2-dimensional homogeneous spaces. So if you want to place the geometric structure on a manifold, it has to be a higher dimensional manifold. So how could it be that you have a geometric structure on some higher dimensional space, but you're actually geometrizing a surface group representation? Well, the most natural way you could imagine that this works is that the manifold M is related to the surface. Say it's a fiber bundle over the surface. So this leads to the notion of a fiber geometric structure. So suppose you have a fiber bundle, M, over the original surface. And suppose you have a GX structure on M. What you could ask for is the fact that the holonomy of the geometric structure, which is a priori a map from the fundamental group of M into G, actually factors through the bundle projection downstairs to the surface group, and you have some commutative diagram, in which case you can conflate the holonomy on the total space with the so-called descended holonomy downstairs, which is just a surface group representation. The first example where this was worked out is quite complicated, so I won't give you all the details, but as an example, the geometric structure could live on the unit tangent bundle of the surface. This was one of the first higher rank examples that was worked out, where G was PSL4R, X was RP3, and these people, Guichard and Wienhard, built a nice moduli space of geometric structures on the unit tangent bundle, and the holonomy actually factored down through the surface. So this is the kind of picture we're after. So I'll say fibered geometric structure when this condition is satisfied. Okay, here's an example, which is kind of a bad example, but it's also a good example because it illustrates a lot of the ideas we're looking for, but it's not a higher rank or higher dimensional space. So let's consider representations, surface group representations into PSL2C, which is just rank 1, but it's okay. And we're not going to consider X to be H3, we'll consider CP1, the boundary of H3. Okay, so what kind of representation should we consider? Well, how about we consider the quasi-Fuchsian representations? These are very well-studied representations, and they can be characterized by the fact that there's a Jordan curve, so a simple closed curve, inside CP1 that's invariant by the representation, and it admits a quasi-conformal parametrization. Okay, if you have such a representation, well, we can geometrize it. There's a very famous theorem about this. What you do is you consider a domain of discontinuity omega by taking CP1 and you remove this set lambda. So topologically, that gives you two disks. And what happens is, okay, that's a domain of discontinuity. And when you take the quotient by the image of the representation, what you obtain are two Riemann surfaces, sigma and sigma bar, of opposite orientation. So what we've seen is that if you have some nice geometric representation, this quasi-Fuchsian condition, then it is the holonomy of a geometric structure. In fact, a pair of geometric structures. It's a holonomy of some complex projective structure on a Riemann surface. Okay, so this gives an illustration of the kind of flavor of what we're looking for. And I guess I'm obliged to say here to tell you about this famous Bayer's uniformization, simultaneous uniformization theorem, which says that the space of all quasi-Fuchsian representations is actually homeomorphic to Teichmuller space, union Teichmuller space of the surface with its opposite orientation. So in fact, you can realize any pair of Riemann surfaces in this way. Very beautiful theorem. Okay, but again, the homogeneous space is just two-dimensional, so there's no fibering here. All right, so now that we have an idea of the kind of schema, the flavor of the theorem we're after, I'll tell you some more. Okay, first I'll tell you some more general ideas about the way this problem is approached, and then we'll start to head towards the actual theorem of today's talk. So suppose you have some representation of a surface group into Lie group G. Say it's higher rank, and maybe it's an Osov. In the standard geometric group theory approach, what you would do is you look for a domain of discontinuity, omega, in some homogeneous space. Maybe it's a flag manifold, maybe not. And your hope under this problem would be the following two things happen. You hope the domain of discontinuity is co-compact, so the quotient is a compact manifold, M, and you could hope that the manifold M is actually a fiber bundle over the surface. And if these two hopes are fulfilled, then the manifold M carries a geometric structure, a G comma F geometric structure, and it's fibered. And this kind of situation has been realized. In fact, there's a really beautiful existence theorem that says there's a lot of these, but very few of them are understood explicitly. Okay, but this is a conference on minimal surfaces, right? So why am I telling you about geometric group theory? I just want to emphasize that this is a standard approach, the way people build these things, and that's not what we're going to do, right? So the broad aim of the talk is to build these fibered geometric structures and to build them using the geometry of some equivariant minimal surfaces. Okay, so that's our broad aim. So now that we have some sort of context, what we're after, I'll tell you the answer to the four questions I stated earlier in the main theorem. So these are the coarse details of the construction. Which Lie group G? Well, today we'll consider this Lie group G2 prime, the split real form of exceptional Lie group G2, which I'll tell you about in the next section. And which representation should we consider? Maybe you can compare this with the previous example. We had some geometric kind of representation to be quasi-Fuchsian. And from that, we saw that that representation could actually be the holonomy. So here we'll consider some kind of geometric representation. And this representation will be the quote, air quote, holonomy of some equivariant minimal surface. In particular, be the holonomy of some equivariant pseudoholomorphic curve in this pseudosphere, which I will tell you about later. And which homogeneous space, which G2 prime homogeneous space will we use? It will be this so-called Einstein 2-3 universe, which for now, all that matters is that it's 5-dimensional and it's compact and it's a homogeneous G2 prime space. So our geometric structures have to live on a 5-manifold. What 5-manifold? Well, I won't tell you for now, but I'll say that it is a fiber bundle over the surface and it has S1 cross S2 fibers. So these are the coarse details of the main theorem. And now we'll get into the weeds, and there'll be many words I need to define later. But so here's the main theorem. So we start off with nu, which is a row equivariant alternating pseudoholomorphic curve from the universal cover of our surface into this pseudosphere, satisfying some generic condition to be defined. Then out of this curve, we will build a 5-manifold, M nu, which is a fiber bundle over the surface with S2 cross S1 fibers. And this 5-manifold carries a fibered G2 prime, Einstein 2-3 structure in the sense defined, such that the holonomy on the total space descends to the surface group, and it descends as the original representation rho, encoding the equivariance condition. All right, so that's a mouthful. But what does the theorem say? It says we can upgrade this equivariant minimal surface in some way to build a developing map on this bigger space, on this fiber bundle over the surface. Somehow we turn this equivariant minimal surface into an actual developing map, which realizes this fiber geometric structure. That's the main theorem. Okay, so now we'll move on and we'll discuss the Lie group G2 prime. But for context, I'd like to discuss how the complex Lie group G2 sits in the, say, the ecosystem of all nice Lie groups. So let's say simple Lie groups, the most primitive kind. So there's a famous classification theorem from around 1900 by Cartan and Killing, which classifies all complex simple Lie algebras. And as one does when you try to prove a classification theorem, maybe you think you have everything, and then you prove the theorem and you realize, oh, there's some extra cases left over. You know, we didn't have everything. So what happens is there are these 4 infinite families of what you might call generalizable type, which are the Lie algebras of the familiar Lie groups, the special linear group, the special orthogonal group, the complex symplectic group, and for various reasons, you separate the odd dimensional special orthogonal group into 2 cases, depending on the odd or even. But then these are called classical type. It turns out there are these 5 leftovers that are not generalizable, that are called of exceptional type, called the G2, F4, E6, E7, and E8, which nobody ever talks about because you can't prove it for infinitely many things, so why would we do it? I think this is the attitude a lot of people have, but there's something very beautiful about this because it's not generalizable. There's some very exceptional special structure here. And the interesting thing about G2 is it sits in this little pocket. It's the lowest in dimension, and it's the lowest in rank of the exceptional guys. So there's some very special structure going on there, but it's tame enough that we can actually get our hands dirty and do explicit G2 geometry in a way that's maybe hopeless to ever do for E8. So that's maybe an advertisement. So let's stay on the Lie algebra side for now. There's 3 different G2s. There's the complex simple Lie algebra G2C from the classification theorem, and it has exactly 2 real forms, the split real form and the compact real form. And so, in fact, every complex simple Lie algebra has at least 2 real forms, and it turns out that G2 has exactly 2. So there's 3 different Lie algebra G2s, which means there's at least 3 different G2 Lie groups. And I'm saying all of this because there's kind of a unified description of each of these, which gives you some context about them and also highlights how the G2 prime stands out. So on the associated group side, there are 3 different perspectives that are all basically saying the same thing, but maybe look quite different on the surface for how you can understand these G2s. The first is through different flavors of octonions. The second is through 3 forms in dimension 7, and the third is through cross products. And I feel obliged to say this because the 3-form perspective is the most common for compact G2 manifolds in special holonomy. But for today, we'll really take the cross product perspective because that's the most adapted to our situation. Okay, so how can you understand these G2s through cross products? You can see it's a very unified definition of all of them. So what do I mean by cross product? What I mean is basically a map that looks exactly like the cross product that you already know on Euclidean 3 space. So that's a map from E3 cross E3 to E3. It's bilinear, it's alternating, and it's orthogonal with respect to the Euclidean quadratic form. So in general, a cross product is some map that behaves similarly, but it's on a normed vector space, and the orthogonality is with respect to that quadratic form. Okay, so over C7, there's a unique quadratic form that's non-degenerate, and there's a unique cross product up to isomorphism, and the complex G2 is just the transformations of C7 linear isomorphisms that preserve the cross product. Now, when you move to the split G2, it turns out that you need to look at pseudo-Euclidean space R34. And here I'll take the convention that the first index in the signature always denotes the space-like, or the positive part, and the second index denotes the time-like part, or the negative part of the signature. So on this R34, there's a cross product. That's this map satisfying these axioms, and G2 prime is exactly the group of transformations that preserve the cross product. And the fact that it's pseudo-Euclidean is related to the non-compactness. Whereas for the compact G2, it's a set of transformations preserving the cross product on Euclidean 7 space. And so that's Euclidean. That's why it's related to the compactness. Okay, so now we have our group, G2 prime. And to be completely explicit, it's the following group, right? You take linear transformations, linear isomorphisms of this 7-dimensional vector space that preserve the cross product. So I emphasize that axiomatically, it's only defined to preserve the cross product and nothing more. although we'll see some other structures come along for the ride. Okay, here's some basic properties of the group. This is a non-compact, split, simple, real Lie group. It's 14-dimensional over R. And although it's defined to only be the cross-product preserving transformations, as I just alluded to, some other structures come along. So the group G2 prime also preserves the quadratic form of signature 3,4, and it also preserves the volume form. So as a consequence, you find that G2 prime is a Lie subgroup of the special indefinite orthogonal group SO34, which is a stabilizer of those two structures. So it's exceptional, but it's really not that bad. You have this beautiful, irreducible, faithful representation in dimension 7, and that's it. You're just doing geometry in dimension 7, and you need to study the cross product. And if you can do that, you can study G2. It's really not, it's not so scary. When you move up to F4, E6, life gets much worse. Okay, so now we'll move on to the pseudosphere. So what is this pseudosphere, S24 hat? It's just the unit sphere, but in our R34 spacetime. So you take the set of vectors so that it has norm 1 under this quadratic form. You say pseudosphere because it's non-compact, and it's a pseudo-Riemannian manifold of signature 2,4. You just restrict the ambient metric as one does, and so that's decoration 2,4 is indicating the signature of the induced metric, right? 2 parts space and 4 parts time. And it's a pseudo-Riemannian space form, has constant sectional curvature +1. But there's lots of pseudospheres, right? You can take any pseudo-Euclidean space, take the set of unit vectors. But what makes this one special is its relation to the Lie group G2 prime. It's a homogeneous space, so G2 prime acts transitively on this guy. But more importantly, it's an almost complex manifold. So there's a canonical almost complex structure, J, on this guy that's coming from the cross product. And here I draw a cartoon where we visualize the same definition in S2, which goes through verbatim. So what is S2? It's a unit sphere in E3. What does E3 have? Has a cross product, and you can visualize the almost complex structure on S2 in terms of the cross product as follows. So choose your favorite point, which I declare for you to be the North Pole, or E3. And then you look at the tangent space at E3, which is the orthogonal complement in the ambient vector space, right? So the E1, E2 plane. And now if you take the cross product on the left with the position vector, that defines a distinguished rotation by pi over 2 in the tangent space. So when I multiply E1 by E3 on the left, right, I get E2. If you imagine doing this construction pointwise, the position vector is telling you how to rotate. And it just happens by accident that this gives you an integrable complex structure because it's two-dimensional surface, so any almost complex structure is integrable. But now when we go to the pseudosphere, we do the same definition, goes through word for word. You define J, the cross product, the almost complex structure at a position vector x. What does it do to a tangent vector y? You just multiply by the position vector on the left. And some cross product identity tells you that J squared is -1. Okay, it's not integrable. So now we have this almost complex manifold, pseudosphere with this J. And from the previous properties I told you about G2 prime, what you observe is that since G2 prime preserves the signature 3,4 quadratic form, it acts by pseudo-Riemannian isometries. And since G2 prime preserves a cross product, it preserves J. So G2 prime is a subgroup of the automorphism group of the pair. But in fact, that's an equality. So if you ask for pseudo-Riemannian isometries that preserve J, that group is exactly G2 prime. So that's another characterization. And now as soon as you have an almost complex manifold, you can talk about pseudoholomorphic curves from a Riemann surface. So here's a nice time to discuss a parallel where we go back to Euclidean 7 space. So think about the compact G2. So use the exact same definition verbatim. You look at the unit sphere inside of E7. E7 has its cross product, that's compact G2 invariant. You get an almost complex structure that's non-integrable on S6, that's G2, compact G2 invariant. So what you should be thinking is, as strange as it may seem, this non-compact pseudosphere S24 hat is just the cousin, it's this G2 prime cousin of the 6th sphere with its round metric. Okay, and Riemann almost complex curves or pseudoholomorphic curves in the 6th sphere have been studied going back to the 80s when Robert Bryant has a famous paper from the early 80s. And on the other hand, these curves in the pseudosphere are rather new. I think the first paper that I know of was from 2010 when Baraglia, a student of Hitchin, wrote a paper where he showed the existence of these pseudoholomorphic curves for certain special representations. And only a few papers have been written. That was in 2010. No, I don't think any other papers were written about this pseudosphere until the early 2020s. So it's very ripe, and hopefully we'll see that there's some interesting geometry going on there. So yeah, my slides were a bit out of order. So here's the actual definition of pseudoholomorphic. So for the rest of the talk, sigma is a Riemann surface on our closed surface S. And I reserve the symbol X for our model space in the GX structures. So you call a curve to be pseudoholomorphic when the standard thing happens. So the differential of the curve intertwines the two almost complex structures. So the map would be holomorphic if the almost complex structure was integrable on the pseudosphere. And sometimes these things are called almost complex curves or J-holomorphic, or maybe people call them holomorphic, but you shouldn't call it holomorphic because it's not integrable. So today we'll make a simplifying assumption that the curve is immersed, although of course you can study curves with branch points, and those are interesting as well. But these will be the ones we're interested in. And all our geometry today is non-compact. We have the split G2, it's non-compact. We have the pseudosphere, it's non-compact. So we don't want to look at maps from a compact Riemann surface. What we are interested in is equivariant maps in the sense which has been described many times now. So we call a map from the universal cover of our Riemann surface into the pseudosphere to be rho equivariant when it satisfies the following equivariance condition. So you precompose the curve by a deck transformation, then the curve changes by post-composition by an element of G2, and you have some representation rho which encodes this equivariance. And by abuse, I might call the rho a holonomy of the curve, but be warned that this is not a developing map of a GX structure because the surface is two-dimensional and the pseudosphere is six-dimensional. So it's not a GX structure in the sense from the beginning of the talk. However, it is a nice equivariant object, and you could hope to upgrade this to an actual developing map on some bigger space. And that's exactly what we'll do in the next section of the talk. Okay, so it turns out there are different flavors of these. Yes? Yes, that's a good question. So yeah, it's not Kähler. It turns out it has this nearly Kähler property, which is actually completely analogous with what happens in the situation with S6. Yeah, the almost complex structure is orthogonal, so you have this Hermitian manifold, but yeah. Okay, so there are different flavors of these pseudoholomorphic curves precisely because the pseudo-Riemannian metric has mixed signature. So you could have a priori a space-like one or a time-like one, and we'll be interested in a specific kind of these curves called alternating, which means it satisfies the following conditions. So recall that we demanded the curve was immersed. So we'll demand that the tangent space is time-like, so signature 0-2 plane everywhere. We demand that the curve is not totally geodesic because there's no differential geometry if it is. So since it's not totally geodesic, you can look at the second fundamental form. The second fundamental form is pointwise a map from the tangent space across the tangent space to the orthogonal of the tangent space. And you can look at the image of that. So the pseudoholomorphic curves are real analytic. So the second fundamental form has isolated zeros. And what we'll demand is that away from the zeros, the image of the second fundamental form is a space-like two-plane. And you can show that this image of the second fundamental form is always two-dimensional. So it either vanishes or it's two-dimensional. Where it doesn't vanish, we demand we get a space-like two-plane. But since the curve is real analytic, the zeros are isolated, and we can extend this two-plane across the zeros. So we have some globally defined, what I may call the normal space. And then I emphasize that for the rest of the talk, if I say normal space, normal line, normal two-plane, I mean this n and not the normal bundle of the surface, which is four-dimensional. But that'll be more clear once you see the next slide about the Frenet frame, which I advertised in the abstract of this talk. So in certain slides, you may see that I put the domain surface as sigma instead of sigma tilde, and that's because equivariance is not relevant, so the remarks just apply in general. So suppose you have some alternating curve, then for any point in the domain surface, you obtain a distinguished splitting of the ambient R34, of the ambient spacetime. What you do is you take the line in the direction of your position vector, and that's a space-like line by definition. Then we demanded that the tangent space was a time-like two-plane, and we demanded that the normal space was a space-like two-plane. And then you could just take the leftover stuff. So take the orthogonal complement of L plus T plus N, and you get the so-called binormal space, which has to be time-like two-plane because that's what's left over. So you'll notice that these subspaces that we got by taking various amounts of derivatives, they alternate in space and time likeness, which is where the name alternating comes from. And what you can do is just record all of these subspaces as a tuple, which gives you some other map, which we'll call the Frenet frame. Just remembers all of these subspaces. And that actually defines for you a different harmonic map to some other G2' homogeneous space, which I will suppress notationally, but the Frenet frame will play a major role in the rest of the story. Okay, so just like we saw the pseudosphere was an analog of the round sphere S6, this Frenet frame is an analog of a Frenet frame you might have seen before, or space curves. Suppose we have some curve gamma from some interval in R to Euclidean 3 space, then there's also a notion of a TNB, Frenet curve, Frenet framing. So make some nice assumption on the curve, say it's a second order non-vanishing, the first two derivatives don't vanish, and you can define a TNB as follows. T is the obvious thing, you take the derivative and you renormalize it, so it's a unit vector. Then you take the derivative of T, and it's orthogonal to T, and you renormalize it, so it's a unit vector. Now you have a pair of orthogonal unit vectors, T and N. You're in Euclidean 3 space. What do? You take the cross product, and that gives you B, and you obtain an oriented orthonormal basis, an SO3 frame for the curve TNB. Okay, so now we have TNB, but you want to do something with it. So it's about differential geometry, right? So what do? You want to take some derivatives. What we do is look at the trivial R3 bundle over the domain and put the trivial connection D on that bundle. And you can decompose the trivial connection along the Frenet framing, T plus N plus B. And what happens is the connection decomposes into pieces relative to that line bundle splitting. You see some diagonal connection nabla, which preserves the Frenet framing. And then you see some tensors on the off diagonal, which are encoded by the curvature kappa and the torsion tau of the curve, which are exactly the isometry invariants of space curves as you learned in the curves and surfaces class. Okay, I'm telling you all this because we want to do the exact same thing in our setting. What we do is cook up the trivial R3-4 bundle over our domain surface. That has a trivial connection D. You can decompose it along the Frenet framing, L plus T plus N plus B. And when you do that, you see the connection takes the exact same form as above. You have some diagonal connection nabla, which preserves the component subspaces, and then you have some tensors on the off diagonal, which are determined by the so-called first, second, and third fundamental forms, which are 1 forms with values in some Hom bundle. For example, the 1 is a 1 form with values in Hom from L to T, which is just a differential of the curve reinterpreted in this context. Okay, so this Frenet framing will play a major role in the story later on. So just keep that in your back pocket. Okay, so now we have all of our background. We have these equivariant alternating pseudoholomorphic curves, and it's time for the main construction. We need to convert these into the fibered geometric structures, as I promised you. So let's recall the 4 questions and their answers in the schema of the main theorem. We fix G to be G2'. We fix rho to be the holonomy of some alternating equivariant pseudoholomorphic curve. And X, I gave you the name, but I hadn't defined it yet. So this Einstein 2,3, this is our model space where the geometries live. This is a space of isotropic lines in R3-4. Okay, so it's a set of lines spanned by a null vector of norm 0 in this quadratic form. This is a 5-dimensional compact homogeneous space. And our 5 manifold, I promised you, is an S1 cross S2 bundle, which I'm about to introduce to you now. Okay, so for the manifold that carries the geometric structures, well, it's actually not natural to write down M on the nose. What you really want is a pi1s cover, which I'll denote by M bar, as I'll reserve the symbol M tilde for the universal cover. Okay, why are we interested in M bar? Well, to answer that, we need to return and remember what is our aim. Our goal is to build a fibered geometric structure. What does that mean? It means the holonomy doesn't really live on the total space. The holonomy only depends on the surface, which means if we had a fibered structure, then we looked at our developing map, which is living all the way at the top of the covering space tower. It's all the way up here on the universal cover. Well, the holonomy would really only descend. The holonomy would descend because it's not doing anything except on the surface. So it would descend to the pi1s cover, m bar. So we want to follow the same reasoning. If we want a fiber geometric structure, what we should do is just build it on m bar in the first place so that we guarantee that there's no holonomy along the fibers and everything is just happening on the surface. So to summarize, building this fiber geometric structure is described by a development holonomy pair where the developing map descends from the pi1m cover, the universal cover, down to the pi1s cover, m bar. So that's a natural space where you should write your developing map down. And that's what we'll do. Okay, so this m bar will be a fiber bundle over the universal cover. So topologically, it's just a product bundle, and it has S1 cross S2 fibers. And we're going to build it inside of the trivial bundle, inside the product of the trivial bundles, R34. But even though the bundle's trivial, what's really matters is the geometry of m bar, the way it's built, because it's carrying some nice structure, which is going to tell us how to build the developing map. Okay, so here's the manifold m bar. Here are the fibers. You fix a point P in the universal cover, and you use the Fernet frame to cook up this bundle. So a point in this bundle, the fiber of a point in this bundle, is a pair, consists of all pairs u and v in our R34 spacetime, such that u is a unit space-like vector in the space-like part of the Fernet frame. So here this notation q plus and q minus denotes a unit space-like vectors and unit time-like vector. So u is a unit vector in this Euclidean 3-plane. So that's chosen in a 2-sphere. And v is chosen as a unit time-like vector in the binormal space. So it's a unit vector in a 2-plane, so that's a circle. There's m bar is a smooth S1 cross S2 subbundle of this trivial bundle, R34 squared. And what I promised you is that there's some natural developing map on this space which takes you over to the Einstein universe. So this is a realization of the main theorem, finally. Okay, here it is. So this map goes from m bar to the Einstein 2-3 universe, which is a space of isotropic lines. And here's the way that works. So dev eats a point in m bar, which consists of a tuple, PUV, where P is in the universal cover and U and V are unit space and time-like vectors in the Fernet frame. And out of those, we need to build an isotropic line. Here's the way you do that. The isotropic line is spanned by the following vector. First, you take U, which is a unit space-like vector. And what you want to add to that is some unit time-like vector, which is cooked up out of a combination of U and V. And if those unit space and time-like vectors are orthogonal, then the sum of them will be isotropic, will span a point in Einstein. So the way you build the time-like vector is, okay, well, you can decompose U. It has 2 parts. U has a part in the normal, and U has a part in the position line. So we call that UN and UL. Take the cross product with V on the right, take some linear combination, and that numerator is a non-zero time-like vector. So you can just divide and force it to be a unit time-like vector. That's what that means. So to summarize, U is a unit space-like vector. The second term is a unit time-like vector. They're orthogonal. So you add them together, it's isotropic, and that gives you a point in Einstein 2-3 universe. So we've parsed the fact that, okay, dev is a smooth map that goes to the Einstein 2-3 universe. And now it's time to recall what does the main theorem say. So here it is. We start off with nu. That's some row equivariant alternating pseudoholomorphic curve, which I said would be generic. And by that I meant it's linearly full, which I'll describe in a moment. Then out of the curve nu, we build the manifold m bar as described. We build this map dev, and I'm telling you that dev is actually dev. It's an immersion, and the holonomy of that geometric structure you've built descends to the surface as the original representation rho. Okay? So just a word on the linearly full condition. What does that mean? It means that the curve cannot be trapped in a codimension 1 subspace. So if you take any 6-plane in the ambient 7 space, you can ask, is the image of nu trapped in this 6-plane? The answer is always no. So the curve sees all directions, that's how you can think. And that's a completely generic condition, as we'll see in a moment. Okay, so given any of these curves, what we obtain is a geometric structure on this bigger space. And the holonomy condition of the curve becomes the holonomy of the geometric structure on this 5-manifold. All right, so what does the theorem say? It says, for every one of these, you get one of those, right? For every curve, you get a geometric structure. So the next question you should be asking me is, well, how many of those curves are there? So that leads us to study this moduli space. You just consider all of the curves. And this was studied in a really beautiful paper by Collier and Toulis. They consider pairs nu and rho, where nu is an alternating rho equivariant curve, and rho is a equivariance, is this representation into G2 prime, up to the natural equivalence. And here you'll notice that I put the domain of the curve to be the universal cover of the surface, not the universal cover of the Riemann surface, which is not a typo, that's intentional, because really the way you should think about it is, what does it mean to be an almost complex curve? Another way to say it is, if it's immersed, the tangent space is J invariant everywhere. And if that's the case, then you can imagine we pull back. We use nu, and we pull back the almost complex structure from the pseudosphere, and we obtain an almost complex structure on the surface. So really, the curve is giving you the almost complex structure. And why do I say all of this? It's because what Collier and Toulis prove is that this space H of S is naturally a complex analytic space, and it holomorphically fibers over Teichmuller space. And the holomorphic projection is the map that I just told you. So you take the curve, it gives you some induced structure, induced complex structure. You think of Teichmuller space as a space of all complex structures, as we've seen, and that defines for you a holomorphic projection to Teichmuller space, which is surjective. Meaning, for any complex structure you want, there's a submoduli of these curves that have that induced complex structure. So this space is really big. There's a lot of curves. The next remark to make is that this is a stratified space. It is stratified by some discrete invariant D, which goes between 0 and 6G minus 6. So there's 6G minus 5 connected components. And what I should say is that as D increases, the fibers get larger, increase linearly in dimension. And the 6G minus 6 stratum is the unique stratum of maximum dimension. Okay, so in particular, the 0 stratum is the smallest, this H0. Okay, so I said that most of the curves are linearly full, and I mean that in a very strong sense. So the curve nu rho is not linearly full if and only if it lives in the 0 component. And in that case, the curve is linearly full in a codimension 1 subspace. So, okay. So to summarize these remarks, there's a lot of curves. So we built a lot of geometric structures, and the construction is robust enough that it works for these different components of curves, which may have some different geometric properties. And the only case it doesn't work is for this sort of degenerate stratum where the curve is not linearly full. All right. So that concludes the explicit discussion. We saw this explicit developing map, which you're probably wondering where that came from. So in this section, we'll discuss a completely different way that you can view the developing map in terms of some other differential geometric objects. So the first new player in the story is a harmonic map to the symmetric space. So again, let nu be any alternating pseudoholomorphic curve, equivariant or not, doesn't matter. And we'll denote blackboard X as the Ramanujan symmetric space of G2 prime. Then if you have one of these alternating curves, what you obtain is a minimal immersion in the symmetric space. Okay, but for us to describe this construction, I need to give you some geometric model for the symmetric space. And the correct model is some sort of fancy Grassmannian. What you do is you look at the Grassmannian of space-like 3 planes in the ambient space, which are closed under cross product. So that's a space-like 3 plane, and you take the 3 plane, you cross product with itself, and it's preserved, it's fixed by that. So the group G2 prime is non-compact, so this is a nice Hadamard manifold, simply connected, non-compact, non-positively curved symmetric space. And the theorem is that by Collier, Toulis, and Ni, if you take any alternating pseudoholomorphic curve, then you get a map in the symmetric space. And well, what's the only natural way you could build it? You use a Frenet frame. So what you do is you just take the space-like part of the Frenet frame. You add together the position line plus the normal space. That's a space-like 3 plane because L and N are orthogonal, and it's closed under cross product because the normal 2 plane is really a complex line. So, okay, that's a point in the symmetric space. Yeah. All right, so now we have an extra object to play with from the pseudoholomorphic curve. We also have this minimal immersion in the symmetric space. And now we're going to need one more object that interacts with both of these. So the next ingredient is a 1 form on the universal cover that takes values in the tangent bundle of the symmetric space along F. Okay, what is this guy? We call him psi naught. You take the sum of the first and third fundamental forms. So recall that we had this trivial R34 bundle over our domain surface. And we decomposed the trivial connection, D, with respect to the Frenet framing. And we saw, previously I wrote it as a matrix, but now I'm writing it as a diagram. It's kind of suggestive Higgs bundle-y diagram. So what you see is nabla preserves the Frenet framing. And the first, second, and third fundamental forms and their adjoints, they move you between the elements of the Frenet frame. And this guy psi naught is just taken as a combination. You just add together the first and third fundamental forms. And for now, you can think that that's some endomorphism valued one form. So one form that takes values in the endomorphism bundle of the flat bundle. But well, really, psi naught takes a very special shape. So it has a more special form than that. So observe that if we take the space-like part of the Frenet frame, P, and we take the time-like part of the Frenet frame, P perp, that psi naught is moving me from the space-like part to the time-like part. First fundamental form moves me from L to T, and the third fundamental form moves me from N to B. So the tangent space of the symmetric space at a point P, you can think of naturally as the linear maps from P to P perp, which are derivations of the cross product. So what you observe is that, okay, psi naught does move me from P to P perp, and you can check that it's actually a derivation of the cross product. So we can refine our perspective on psi naught to say, well, that's a one form on the universal cover with values in the tangent bundle of the symmetric space along F. Okay, so now we have three objects. We have the curve nu, we have the map to the symmetric space F, which is some sort of Gauss map of nu, and we have this guy psi naught. And our goal is to describe the developing map in terms of psi naught. Okay, so we're going to understand the fibers of the developing map in terms of psi naught. So fix a point in the universal cover. And what we want to understand is, how does dev look like when we restrict? We restrict to a fiber, which is S1 cross S2. We have some map to the Einstein 2-3 universe. Well, it turns out that the developing map is not quite injective on fibers, but almost. It's 2-to-1. And you can explicitly see what is the image of that developed fiber in terms of psi naught. This is actually closer to how the proof of the theorem goes, taking this perspective rather than the perspective in the last section. Okay, so for me to describe what the developed image of the fiber is, first we need to actually understand how to see in Einstein 2-3 universe. So far in the talk, all I've done is just give you a definition. It's a set of isotropic lines. I need to give you some model, some way to conceive of this space. But I'm going to do better than that. I'm going to give you a family of models. And it's going to be important that we have this flexibility to view the Einstein 2-3 universe from these different perspectives. Okay, so here's a bunch of models. What you do is you fix a background piece of information. You fix a space-like three-plane, P. And relative to P, you get a model for the Einstein universe. And I call that model FP. So the model goes like this. It's a map from the unit sphere in P across the unit time-like sphere in P perp, which is topologically S2 cross S3, over to the Einstein 2-3 universe. And what you do is you take the pair UV of unit, space, and time-like vectors, and you add them together. They're orthogonal, so that gives you an isotropic line. And the statement is that this is a 2-to-1 smooth covering map. And moreover, the pre-image of a point in the Einstein universe is exactly a pair of antipodal points in this product of spheres. Okay, so as a consequence, you see that the Einstein 2-3 universe is diffeomorphic to this product of spheres, but we have to quotient by the antipodal map. Now here I really want to emphasize the distinction between the intrinsic and extrinsic perspective. So extrinsically, sure, Einstein universe is product of spheres and you quotient by some Z2 quotient. But really the point of the proposition is intrinsically, what are those two spheres? And you see those relative to P. And that's going to be important for the picture. So here's the idea. We're going to understand the developed image of the fiber in terms of the model for Einstein 2-3 via the corresponding point in the symmetric space. So recall little p was a point in the universal cover. We want to understand how does this fiber develop. And what we do is we take the little p in the universal cover, feed it into the map to the symmetric space. That gives us a three-plane big P. And we're going to see the fiber in that model. Okay, so if we take a generic point in the Einstein 2-3 universe, L, then by the previous proposition, we can write it as the span of some vector, and the vector is a sum of two guys, u and v. U is a unit space-like vector in this plane big P, and v is a unit time-like vector in P perp. That's just an arbitrary point of the Einstein universe. So the question is, in this model, when does L lie in the developed image of the fiber? And here's that criterion. So point L in the Einstein universe, written as a sum u plus v, lives in the developed image of the fiber over little p, if and only if the following condition is satisfied. You take all tangent vectors to the universal cover at little p, you feed those tangent vectors into psi naught, and that becomes an endomorphism. So psi naught of x will move u from space to time, and then you can take the dot product between psi naught x of u and v. And what you demand is that you get 0 for all tangent vectors. And if that condition is satisfied, then this line L lives in the developed image of the fiber. So you see psi naught is telling you everything. Okay, so here's another picture, another way to see that. What you can think of is if we fix the space-like vector u, we can consider our psi naught at u, which you can imagine as the bad directions, what we want to avoid, which is you take u and you just push it over to the time-like part by psi naught of x across all tangent vectors. Those are all the directions we want to avoid. And that actually gives you a vector bundle over the unit sphere in P. And it's a trivial vector bundle. So here's a picture. You fix the unit space-like vector u, and you want to know what are the good directions and the bad directions for u. So you take u, you push it over by psi naught, and that gives you some bad two-plane, which I drew in purple. And that gives you a complementary good two-plane, the orthogonal complement, which are the allowed directions for v to move in. So this is a kind of cartoon. And the summary of the previous slide is that the developed image of the fiber admits the following description. It's a set of lines, u plus v, where u lives in the space-like part of the Frenet frame, and v lives in the good directions relative to u. So this r psi naught at u perp. So u is chosen in a two-sphere, and v is chosen in a circle. But what you remember is that in the Einstein universe, we have this antipodal map we have to quotient by. So the developed image of the fiber is a product of spheres quotiented by this antipodal map, which is actually a copy of some smaller Einstein universe, Einstein 2.1. So the summary of this whole section is that if we replaced our manifold M bar by taking some Z2 quotient, so that has Einstein 2.1 fibers instead of S1 cross S2 fibers, then the developing map would be an injective immersion on fibers. So the key to prove that you actually have an immersion is to understand how those fibers are moving. And we saw that the fibers are completely determined by psi naught. So essentially, you need to understand how psi naught is moving. And that's really the very key ingredient. All right, since I have a little bit more time, I can get to the final section. This is a bonus section. This is a question that should be on your mind. So I was alluding to this at the beginning. One feature I think is very interesting about this geometric structures problem is that it's kind of a chicken and egg thing. How can you have the manifold M? You're trying to find how to geometrize the representation, but you kind of have to know the answer to even make the construction. You need to know what M should be. But how can I know what M should be? I'm trying to figure out how to geometrize it. Well, in this case, we kind of did know the answer, and that was what made everything work. So I'm going to explain where this choice of S1 cross S2 came from. You know, there's lots of three manifolds. Why is this the right one? Well, the answer is related to the Hitchin component. So what's the Hitchin component? It's a connected component in the representation variety, where G is a split real simple Lie group, like now your favorite Lie group, G2 prime. Okay, so Hitchin defined this in 1992. There's a distinguished embedding of Teichmuller space inside the Hitchin component called the G-Fuchsian locus. And why is the Hitchin component interesting? Well, it's interesting for many reasons. For the most part, because we have these analogies with Teichmuller space. So there's various perspectives on Teichmuller space, but for now, I want you to view it as, in fact, it's a connected component in the character variety, in the representation variety of PSL2R. So from what we saw earlier, this Teichmuller space is exactly the holonomies of these hyperbolic structures on the surface. Every representation in Teichmuller space is irreducible. Teichmuller space is well known to be diffeomorphic to a cell. Every representation in Teichmuller space is discrete and faithful, as we saw. It's the holonomy of a hyperbolic structure. And in fact, The fact that it's discrete and faithful in the rank 1 setting is equivalent to those representations being a Nosov. And so when Hitchin defined the Hitchin component in 1992, which he tried to call the Teichmuller component, but the community rejected his name and called it the Hitchin component, what he proved is that he proved some remarkable analogies. So what Hitchin proved is that every representation in the Hitchin component is irreducible, and the Hitchin component is diffeomorphic to a ball as well. But moreover, he gave a beautiful parametrization of the Hitchin component in terms of holomorphic differentials on some background Riemann surface. In analogy to how we've seen this week, you can understand Teichmuller space as a space of holomorphic quadratic differentials on some background Riemann surface. But even more amazing properties happen. This was not known to Hitchin at the original time, but in 2006, Laborie and Fock and Goncharov independently proved that every representation in the Hitchin component is discrete and faithful. So this leads to the notion of what people call now a higher Teichmuller space, which is a connected component in this representation variety where every representation in the component is discrete and faithful. And the Hitchin component is one of the main families of examples. And in fact, when Laborie was studying and proved that every representation is discrete and faithful in the Hitchin component, that was what led him to define an Nosov representation. This is really where a lot of the core ideas of the field come from. Okay, why am I telling you about this? It's going to come back, I promise. So let's take a Hitchin representation to G2 prime. Such a representation satisfies some Anosov condition of some flavor. Okay, and because of that, you can invoke this theorem of Guichard and Wienhard from 2012, which says that there is a domain of discontinuity for this representation in the Einstein 2-3 universe. So you can follow this geometric group theory approach. Try to find some geometric structures for the G2 prime Hitchin component. And they conjectured in the original paper that the quotient is a fiber bundle over the surface, and that conjecture was affirmed last year by my collaborator, Colan Devallo, and a bunch of people, Alessandrini, Maloney, Tolzon, and Wienhard. This theorem is much more general, but applies in this setting. Okay, so now we have the Hitchin representations. We know they're Nosov. They have this geometric structure, and it's fibered. Our hopes, our best hopes are satisfied. The representation admits this fibered geometric structure. So what is it? Okay, so the first thing, actually at the very beginning of my project, I told you the story completely backwards in the talk. The first thing that Colan and I proved is that if you take a Hitchin representation, then the fiber of the geometric structure is Einstein 2-1, which is the same fiber that we used. So what that told us is that out there, somewhere in the world, is some 5-manifold with Einstein 2-1 fibers, and it carries the fiber geometric structure we're after. And so we went in search of that, but our theorem is much more general. It works more than just the Hitchin representations. And I remarked earlier that we had this stratification of the space of pseudoholomorphic curves, and this 6G-6 stratum was the biggest one. The 6G-6 stratum is actually exactly the Hitchin component. So our construction builds geometric structures for Hitchin representations. Okay, and so the last thing I'll say is, okay, then there's a question about how our construction is related with this domain of discontinuity that the Guichard and Wienhard built. So here is a story coming full circle. So if I take a Fuchsian representation, so that's a representation in the Hitchin component that sits in this distinguished copy of Teichmuller space, then there's a unique row equivariant pseudoholomorphic curve by Collier and Toulis. So you can take that curve, you can build the manifold M bar, you can build the developing map that I described to you, and what we find is that the image of that developing map is exactly the Guichard-Wienhard domain, and the developing map is a covering map onto their domain, which almost certainly is one-to-one, but we haven't proved it yet. So in the end, we find that the geometric group theory approach is really saying the same thing as our differential geometry approach, but we're able to actually realize what the construction is explicitly using these equivariant minimal surfaces. So I'll end the talk here. Thank you very much.
Thanks, Barker. So questions, please.
So maybe I missed this. What's the set of holonomy representations of these alternating these ones there? Is it? I mean, it includes all the Hitchin ones, but then,
yes.
How big is it? Or?
Yeah, this is an excellent question. So actually, in Collier and Toulis's paper, when they define the moduli space, what they say is, well, the representations, we had this stratification. The 6G-6 stratum the holonomies of those curves is exactly the hitching component, and you obtain actually a diffeomorphism there. And the 0 stratum contains within it representations in the SL3R hitching component off of the Fuchsian locus there. But for everything in between, for D between 1 and 6G minus 5, nobody has studied these representations before. So in the paper, Collier and Toulis, they prove some infinitesimal rigidity statement, which says basically the holonomy map. So you saw that we had this moduli space of pseudoholomorphic curves, which carries the nu and the rho. So there's a natural holonomy map to the character variety, which just forgets nu and takes rho. They prove this map is an immersion, but in general, the strata are not open. They're of lower dimension. So on the hitching component, they obtain a diffeomorphism to between the 6G minus 6 stratum and the hitching component, but on all the other strata, they're lower dimensional. So we don't know if the map is injective, and we don't know how to characterize the other representations besides the sort of top stratum and the bottom stratum. But that's, yeah, something very interesting and something I'd like to think about.
Maybe I'll ask one more question.
Yeah, please.
So for these Anosov, there's also this limit map.
Yes.
So is there like this will be the boundary of your domain or something?
It must be.
Okay, it must be. I see.
Yeah, and yeah, you're driving at a great question, which is, it seems like, okay, you have this rho equivariant surface, and it lives in the pseudosphere, and actually the boundary of the pseudosphere, you can projectivize it, then it lives in RP6. And the boundary of the pseudosphere, well, what happens when you degenerate a positive line? Becomes an isotropic line. So the frontier of the pseudosphere in projective space is the Einstein 2-3 universe. So as you say, we have this equivariant curve. It just must be the case that the boundary is some equivariant circle, which is the Anosov limit map. And it must be true, but it's actually not so easy to prove that. But another one of our results, which I didn't get to mention, is that we can actually prove that some of these representations are Anosov using Higgs bundles, which is kind of phenomenon that's only emerged in the last few years, starting with a paper of Simeon Philippe from a few years ago. So some sort of special strata of these pseudoholomorphic curves, the ones that are super minimal, we can prove that they're actually Anosov. And it's still a work in progress, but we should be able to prove for those curves that actually it is the boundary, that sort of these curves do extend to infinity, and the Anosov limit map is the boundary of the curve.